Hello again, and welcome to our next abstract algebra video. This is the first one in the second section of Chapter 0 on modular arithmetic. You've all had the proofs class before. I don't think anyone in this class has had, maybe one person has had number theory before or two. So for those of you who have, this will be familiar, but if you haven't, this might be sort of new, but I imagine it's gone over in the proofs class as well. One thing I do want to mention about how we do modular arithmetic in this book is they actually introduce it with two different definitions, which is a little bit unusual. Most books don't do it that way, but there is some value to it, and I'll explain both definitions. The first is the one that just this book uses, and the second is pretty common to a lot of books. So hopefully it'll all make sense. If anybody has any questions, you can email me or contact me through the Google Hangouts as well. All right, so let's get started. Modular arithmetic is essentially dealing with arithmetic on remainders is the general idea. You'll look at this and find that most of the things we do in arithmetic normally still work when we're just dealing with remainders, so it shouldn't be a problem. But let's start off by looking at their definition, the book's definition of what they call A mod n. And this is a little bit awkward because the standard definition that most books use, and this book uses later on, is called congruence mod n, which is A congruent to B mod n. But this book uses A mod n as a separate definition as well. So this is the one we're going to start off by looking at. And our definition of this is if A is an integer and n is a positive integer, n can be 1. It can be bigger than 1 as well. It's rarely going to be 1, but if it's, as long as it's positive, it'll work. We call the remainder when dividing A by n. So the remainder when dividing A by n by the name A mod n. And we call this process, and the book doesn't use this, but I do fairly often. So if I mention reducing mod n, what I'm actually asking for you to find is A mod n. So if you have the number 18 and I ask you to reduce it mod 5, I want you to find 18 mod 5 is the idea. Okay, so that's our first definition, and really all this involves is using the division algorithm, or if you want to think of it this way, using long division like you used in grade school. So let's actually start off by looking at some examples of this before we get into congruence mod n. So I've got these examples down here. I'll leave the whole screen up for just a little bit. What I want you to do is find the remainders of, essentially find 27 mod 15 minus 16 mod 3 and 37 mod 7. So you're looking for the remainders when you divide A by n. The second one might be a little bit tricky, but we do have a way to get through that. Really all you have to do is use the division algorithm, but if you have a little bit of trouble with that, I'll explain. In any event, pause the video and work through those, and when you come back, we'll go through them. All right, if everybody's back now, let's take a look at these and sort of how you can do them quickly. Let's put this in blue. So 27 mod 15, here you can actually long divide very easily. You take 15, divide it into 27. 15 goes into 27 once with 12 left over. So that's our remainder, and that's 27 mod 15. Another way you can do this, and I'm pointing this out mainly because it's going to be helpful for the second case, or a related idea is helpful for the second case. Instead of just long dividing, another thing you can do here is you can subtract the largest multiple of 15, or n if you have a general example. Subtract the largest multiple of 15 you can from 27, or here in this case, we're in general, or a, that still leaves a positive result. So that's another way you can do this without going through the whole process of long dividing. It doesn't matter here in one like this. It's really simple to long divide. You just divide on, you can even divide on your calculator, find the whole number part, that's the quotient, multiply that by the mod, and subtract, and that's what's left over. So you can still do that. The second one is where this gets a little bit trickier, and a process like the one we did for the first one also works for the second one. And so let me say what we should do here. Here, instead of subtracting, we can add the smallest multiple of 3 that still leaves, or that, sorry, doesn't still, that gives a positive result. So here you can add a multiple of 3, whichever is the first multiple of 3, the smallest multiple of 3 that makes that positive is the one that you want, and you add that, and what you get is the remainder. So here, if I want a multiple of 3 that I add to negative 16 and get a positive number, that would be negative 16 plus 18, which would leave me, would leave me 2 there. And lastly, 37 mod 7 is pretty straightforward again. You can just do this by long division if you want. 7 goes into 37 5 times. You subtract 35 and you're left with 2 as your remainder again. Not all remainders have to end in 2. These ones just happen to. All right. So that's how you reduce mod n. And since this is the book's questions, they'll probably refer it to you in terms of a mod n, but generally I would use this terminology here, reducing mod n, rather than just calling it a mod n, because when I refer to a value, a variable mod n, I'm usually talking in terms of our next definition, which is congruence. Okay, so hopefully that helped. If anybody has any questions on that, you can feel free to contact me anytime. Let's go. Oops, sorry, wrong. Okay, it doesn't seem to want to. There we go. Okay. So our next definition is congruence mod n. And here, this is a definition that's related to the first one, but you might not see initially exactly how it is. Here, if now we have two integers. They don't have to be positive, they can be anything. And we have a third integer, n, which is positive, which is the mod that we were talking about before. We call that the modulus, is also in other terms. We say A is congruent to B modulo n, or we generally write it in this form: A congruent to B mod n, and generally we'll use that triple equal sign. That's pretty common for congruence mod n. We say this if n divides the difference b minus a. Now here you'll notice I say b minus a rather than a minus b, proving that a is congruent to b mod n if and only if b is congruent to a mod n is really simple. You just have to show that if n divides b minus a, n also divides a minus b, and you just use the definition there. I don't think I'm going to do that proof today, although I will do a couple proofs here related to congruence. The first one I've got down below, and we'll talk about that here in a second. But this idea is where essentially modular arithmetic comes from. You have to be able to have if you have two values that are congruent mod n, they have to behave the same way in terms of a lot of different properties, and you can actually prove pretty much all of your standard properties work. We're going to do one example, which is addition, and I've got a theorem down below, but you can actually do this theorem with subtraction, which would be exactly the same as what I've got written here, or multiplication, which is the proof's a little bit harder, but it still works. So let's go ahead and use this congruence proof here to prove the theorem that we've written down below. Now, before I have you all pause the video and get into that, let me actually type this out. Let's remind ourselves what kind of proof this is. So this theorem is an if, let's make that bold, then proof. And as we talked about last time, you assume the if part and use that to prove the then part. All right, okay. Let's actually make these. Let's capitalize these, because that's the important thing, right? All right, so here we go. So we assume the if part, use that to prove the then part. And as with a lot of proofs, after you do that, you will want to start restating things in terms of their definitions, and you might have to do that several times. It's a fairly common way to prove things. You'll hear it called chasing definitions sometimes. Go ahead. So that'll be the next few steps. So what I'd like for you all to do is, again, pause the video, try and either prove this theorem if you can, or at least set out the first few steps of it. And remember, we've already got the guidelines here for an if-then proof. For an if-then proof, we assume the if, and then prove the then part. Okay, so that's what we want to do here. So go ahead and pause this, and when you're done, you can come back and we'll show how this is proved. Okay, if everyone is back, let's go ahead and prove this result. Bold again. Oh, actually, hang on. I'm not going to use that. I'm going to use writing because it's actually, I actually like the triple equal sign a lot. It's going to save me a lot of writing, so I'll use that instead. So here we're going to start with the if part, and the if part tells us A is congruent to B mod n, and C is congruent to D mod n. So those are the two things that we have for the if part. So that's where we're going to start. Let me go ahead and put that in here. I'm going to have to blow this up a little bit because it's easier for me to write if it's really big. Assume, so we're going to assume two things, the two if parts. Here, oops. So assume A is congruent to B mod n, and C is congruent to D mod n. So hopefully you all got this part from the guidelines I gave you. So this is our first line of the proof. We want to assume, or probably suppose is a more common term to use there, but we're assuming A is congruent to B mod n, C is congruent to D mod n. And remember, we want to show A plus C is congruent to B plus D mod n. So that's what we want to show. So from here, like I said, at this point we need to deal with the definitions of the definition of congruence. And so if we want to look at that, we can go back up here. A is congruent to B mod n if n divides the difference, B minus A. So we can use that here to get our next line. So we can say then, hang on, wrong one. Then by definition, I'm going to abbreviate this DEFN. That's a fairly common abbreviation for definition. So by definition, n divides, I'm going to use the symbol here rather than writing it out, n divides B minus A. And again, also n divides, think here, should it be C minus D or D minus C? I know it doesn't really matter, but according to our definition, which one should it be? Well, it is D minus C. Like I said, it doesn't really matter because you can actually prove that the definition is equivalent to the n dividing the reverse order. So we get that by definition. Now, unfortunately, that's still a little bit hard for us to use. We can go a step further and use the definition of divisibility. So let's go ahead and do that. So since n divides B minus A, that means B minus A equals nx for some integer x, and D minus C equals ny for some integer y, or for some integers x and y. Okay, so that is what we get here. That is At this point, I was expecting you all to be able to get at least to about here without me helping you, just from the reminder of how we do an if-then proof and knowing these definitions. So that is where we got. Now we aren't done. We still have to do what we're going for, and at this point it's probably a good idea to put a we want to show in here just to remind ourselves where we're headed. We want, well, that wasn't what I wanted. We want to show sorry about zooming in this much, but you know, that's the way it goes. We want to show what was it? B plus D is congruent to A plus C mod n. And remember here, it's useful to think of this again in terms of the definition of congruence mod n. So we want to show B plus D is congruent to A plus C mod n. Now, if you have gotten this far, but you didn't finish the proof off before, I'd like for you to pause the video again and think, how could I get there from these two statements that I already have here? B minus A equals NX and D minus C equals NY. There's a little bit of work that you have to do. It's not very complicated though, so go ahead and pause and see if you can get that if you haven't already done so. Okay, so we're back. Then the next thing we want to do is we want to do B minus A equals NX, and I'm going to write D minus C equals NY, and as you might have guessed, I am going to add these two together. And I'm adding them vertically because that's what I do. Alright, so B minus A plus D minus C equals NX plus NY. Alright, there we go. Zoom back out. Okay, now, one more step here. Remember, we want to show this. We want to show B plus D is congruent to A plus C mod n. So what we're going to do here is we're just going to rearrange this statement that we've got here. This statement that we just found. So, I want, is that what I said here? Oh, I actually reversed those, didn't I? Come on, man. Alright, hang on. Like I said, it doesn't matter, but let's go ahead and fix this anyway. Okay, so this should be, A plus C congruent to B plus D mod n. Sorry about that. Like I said, this doesn't actually make any difference because it's easy to show that congruence works either way, but just so I have it according to the definition, I wanted to rewrite it there. Okay, so let's go ahead here. Then we should have B plus D minus A plus, come on man, plus C equals N times X plus Y. And again, sorry about zooming in, but you know, it's better to have it readable at the end when you have the PDF than not. So here we've just rearranged the line above. So we've rearranged this line to get the new line, just put the b and the d together, the n and the c together, and factored the n out of the right-hand side. So that's all there is to that. And that actually tells us what we wanted to know. So that tells us so n divides b minus d minus a plus c so that gives us our proof. What was it? A plus C congruent to B plus D. Come on, there we go. B plus D mod n. I guess I don't actually need that. Let's get rid of those parentheses there. Okay. Oh, the other thing up here, I had a B minus D there. It should have been a B plus D. So just so you know, that's how that changed. So n divides that difference. So that means those two things are congruent, and we're done there. Okay. And that's all there is to that proof. Now, there is one other thing that I want to sort of briefly talk to you about here. That is, you'll notice that this first definition that we have here, we call the remainder when dividing a by n, a mod n. So the one question you might have is that remainder actually equal to, is that remainder actually congruent to a mod n? And the answer is yes, it is. And let's actually explain why. Let's go. Let me actually do this down here. Okay. Another theorem. This is really short, so I'll just do it really quick. Theorem. A mod n is congruent to a mod n. I know this is a weird way to phrase it, but when you have two definitions that are virtually described using the same terminology, but they mean different things, it does get a little bit awkward. So we're going to say here a mod n is congruent to a mod n. In other words, remember this one right here, this thing right here, is our remainder r from the division algorithm. So that's our remainder. Okay, so let's do a quick proof here of this. And all there is to this proof is using the division algorithm, actually. Okay, so here, by the division algorithm, let me capitalize it. It's important, right? I don't make you all leave your names uncapitalized, so the division algorithm deserves the same respect. All right, so the division algorithm, we can write, no, okay, this is a little bit awkward. NQ, thanks autocorrect, plus R, where 0 less than or equal to r less than n is our remainder, and r equals what we're calling a mod n. So r equals the reduced version there here. Now let me make that the less than or equal to, like I like. Okay, so by the division algorithm we can write a equals nq plus r. Let me give myself a little bit more room here. Okay, so we've got that. Rearranging gives us a minus r equals nq. So n divides a, use parentheses here, n divides a minus r. In other words, a is congruent. I'm going to use an equal sign here and just convert it to a congruent sign. R. Let me make sure. No, I guess I would say R is congruent to A mod n. Again, not that it matters. And that is all we have to do for that proof. Oh, hang on. I messed this up here a little bit, but let's... There we go. That's a little bit better. Okay, so let's get rid of that. Let's put it where it needs to be now so you all can see it when you have this PDF. And this one goes right there. Okay, so really all you have to do is reorder the division algorithm and you're done there. That shows you that your remainder is congruent to the thing that you divided by n in the first place. All right, and that is pretty much it for this section. They have some stuff in there on uses of modular arithmetic in security stuff. I may talk about that, but I'm not actually going to ask you to do it, so I'm not going to go into that in this video, and I think that's it for this section. If you have any questions, remember to let me know. Hopefully, unlike the first time I did this video, this time it will record and I'll be able to upload it. So cross your fingers for me, but of course, when I say cross your fingers for me, if you are hearing that, your fingers don't need to be crossed because my luck has happened in the past, right? So, crossing your fingers would be too late. Let me see if this lets me do emojis. I bet it will. Where's the cross fingers emoji? There we go, crossing fingers. There we go. And also the guy puking, and the devil, And what else? Where's the superheroes? Oh no, some rock stars. There we go. There we go. All right. So hopefully you all can follow that. It's pretty clear what I'm trying to say there. I don't want to punctuate that. All right, there you go. So, hang on. There we go. There we go. All right. So remember that it's a lot easier to do emojis than draw. Anyway, I will talk to you on the next video, and hopefully this made sense. Please let me know if you need anything, and I will talk